Well, good morning, ladies and gents. On Friday, we started with related rate of change, and this is just the rate at which y changes with respect to x. And there's a formula that will help us on the way there. It is dy dt times dt dx, and we can see that the t and dt can cancel out, and that would give me a result of dy dx. Or the formal formula that will be on your formula sheet is dy dx equals dy dt divided by dx dt. And both of them are very useful. Both good. Let's start with inflating of a balloon of two problems. A spherical balloon is being inflated. The radius of a balloon is increasing at the rate of 1 centimeters per second. Find the rate of the volume of a balloon when the radius is 8 centimeters. Well, let's see what can we do about this. I'm sure that there's some bits here that we haven't read nicely. A spherical balloon. That means that the balloon is a sphere, okay? And we know that we want to find it in terms of volume. So let's see, what is the volume of a sphere? It's 4 over 3 pi radius cubed. Good. Whenever I find this volume, I'm just going to take, because we don't want the rate, we don't want volume, we want the rate. So I'll just take the derivative in any case, dv dr, maybe we will need it, equals 4 over 3 pi times 3 pi squared. I can simplify that. Let me move my paper up to 4 pi radius squared. So this is dv dr. Good. So now, what are some of the givens that was given? The radius of a balloon is increasing at a rate. It is radius, so it would be dr dt, because it's per second, would be 1. Okay, now what do they want me to find? Find the rate of a volume when the radius is 8 centimeters. So we want to find dv at a particular instance. It must be per time. It will be at a specific time. So that's what we want to find, dv dt. Okay, let's see what can we do about these. Okay, so I need something to string up. I want something in the numerator to cancel out of something in the denominator. I've been given, I have a dr here, and I have a dr there. If I cancel the drs, I'll be left with dv dt, and that is exactly what I want. Okay, let's continue there. We have the r that can cancel out, and it will be leaving me with the v dt, and that's exactly what I want. So let's write it down. Okay, so we know that this dv dr times with dr dt will give me a result of dv dt, and that's the one that I want to find. Okay, let us substitute those values in. dv dt is the one I want to find, so I have nothing for it. dv dr is 4 pi radius squared times the r dt. The r dt is 1 when the radius is 8 centimeters. When r equals 8, so that's 4 pi 8 squared times 1. And if I type that into my calculator, I get 256 pi, and that is my final answer. Good. Let's continue with the next question. The area of a ripple. Okay, a stone is dropped into a lake creating a circular ripple that will travel outwards at a rate of 60 centimeters per second. So this is a rate. A stone is dropped and it will find the rate. It's also a rate that we want to find, that the area of a circular ripple will increase when the radius is 4 centimeters. Okay, so let's see what can we find. Okay, I know that a circle have an area, and that area is pi radius squared. I can find the r dA. That would be the derivative of a with respect to r. So the a dr, okay, equals 2 pi r. That is something that I know, okay? Just from knowing that I need to find the area, the rate of the area, okay, when r is 4. So I'm just writing down it all in script. So what is that, what they've given me? The rate that the circulars travel is at 60 centimeters per second. So it must be in terms of the radius. So dr dt equals 60 centimeters per second. I'm dropping the measurements over here so that it makes it a little bit easier to work with in the problem. Okay, so do we have enough? What do we want to find? Find the rate that the area will be increasing at that specific moment, or at when the radius is 4. So we want to find the ADT. Okay. The A, the R, that will leave me with the ADT, and we have an R on the radius. So I can string this up. Can you see that? The R can cancel out. It will leave me with the ADT, and that's what we want to find. Okay, so the ADT, the derivative of y of a rate at which the area changes with respect to time, would be the ADR times the R dt. The R and the R can cancel out, but let us first substitute the values in. The ADR was 2 pi r, and the R dt is 60. Good. So when r equals 4, I just need to substitute 4 into my equation, use my calculator to find the answer. That would give me 2 times 4 times 60. That would give us 480 pi. Okay, and that is the final answer, and we are done. Good, ladies and gents, I'm glad that I could spend a little time with you. There's just one of the questions that one of the students asked out of a previous exercise that I'd quickly to look at and give you some feedback on it. It was from exercise at 7A in your textbook on page 96, and she said, well, she's not quite sure about 2e. Okay, so we have a function fx, and that function is the square root of x, and then it has the constraints x must be greater or equal to 0. Okay, and then the question is find the derivative of this function. And it also asks us to draw the function. Okay, so we know that this function fx will have will look something like that. Okay, so now let's see. If I need to find the derivative of this function, first of all, I need to change this into an index form. So fx equals x to the half power. Then, if I need to find the derivative, I would just use my rule. So fx equals ax to the power n. If derivative will be a times n x n minus 1. Okay, so we need to apply this rule. Sorry, that negative 1 can't disappear there. Okay, so f prime will be a half times 1 would just give me a half x. A half minus 1 would just give me a negative a half. Okay, you can use a variety of ways to plot this graph or to see how the behavior of a graph will be. If we just have a quick look, if I have a really small value, like when x equals like 0.01, okay, what will happen to this function? So I have 0.5 and then 0.01 to the power negative 0.5, and that would give me a value of 5. So when x is 5, my f prime of x would be 5. Okay, or my y value would be 5. So let's take a look at if it is some smaller number, so 0, 0. Then it will become quite larger. So if 0.00, do I have another 0? 0.1 would result me a 50. Okay. Okay, so but what about values that is a little bit larger? Say 1. That would give us a half. And I take an even bigger number, say 5. I get a smaller number, 0.2. And if I take say 100, I will get a really smaller number. So f prime of 100 is 0.05. Okay, and therefore we can deduce that this function will have a look like something like that. It will, as it increases towards the towards the 0, or as it pushes along to the y-axis, this function will increase. Okay, and as it gets larger, the values of x gets larger and larger, the function will gradually get smaller and smaller. And that would be a rough estimate on the idea of how does this function behave, the end behavior of this function. However, if you want to go and play a little bit around on how the functions will look like, please go on Desmos. It's a graphing calculator on your computer, and then they will give you the answer of how this function will look like. I hope this was of value of you. Enjoy your even afternoon, and I'll see you tomorrow.